What if I told you that one man, a quiet, rebellious thinker, changed the way humanity understands time, space, and reality itself? A man who failed school exams, who struggled to find a job, and yet would go on to rewrite the laws of the universe. His name was Albert Einstein. This is not just the story of a genius. This is the story of curiosity, imagination, and a mind that refused to accept the limits of conventional thinking. In the middle part of his career, Einstein made important contributions to statistical mechanics and quantum theory. Especially notable was his work on the quantum physics of radiation, in which light consists of particles, subsequently called photons. With physicist Satyendra Nath Bose, he laid the groundwork for Bose-Einstein statistics. For much of the last phase of his academic life, Einstein worked on two endeavors that ultimately proved unsuccessful. First, he advocated against quantum theory's introduction of fundamental randomness into science's picture of the world, objecting that God does not play dice. Second, he attempted to devise a unified field theory by generalizing his geometric theory of gravitation to include electromagnetism. As a result, he became increasingly isolated from mainstream modern physics. The man known to history as Albert Einstein was born on the 14th of March, 1879, in the city of Ulm, in the south of what was then the German Empire. Ulm was a major urban center of the Kingdom of Württemberg, a major constituent part of the German state in the late 19th century. His father was Hermann Einstein, an Ashkenazi Jew from Buchau in Württemberg. Before Albert Einstein became one of the greatest scientific minds in history, his worldview was quietly shaped at home, within a family that blended engineering ambition, artistic sensitivity, and intellectual curiosity. Albert's father, Hermann Einstein, was an engineer and entrepreneur living at the dawn of Europe's electrical revolution. In Munich, he co-founded the company Elektrotechnische Fabrik H. Einstein and C.E., which manufactured arc lamps, dynamos, and installed modern lighting systems across southern Germany and parts of northern Italy. For a time, the business thrived, riding the wave of technological optimism that defined the late 19th century. But progress was unforgiving. As industrial giants like Siemens and AEG expanded their dominance, Hermann's smaller company struggled to survive. Financial pressure mounted, and eventually the business collapsed. The setback forced the Einstein family to leave Munich, first relocating to Milan, then to Pavia, a period marked by uncertainty and constant movement. Despite these hardships, Hermann played a crucial role in shaping Albert's early fascination with science and engineering. He took his son to factories, exposed him to machines and technical problems, and supported his education even as the family faced financial instability. Though Hermann continued searching for work in the electrical industry, he never regained his earlier success. He died in Milan in 1902, while Albert was still a student in Zurich. Albert's mother, Pauline Einstein, provided a very different but equally powerful influence. Raised in a cultured, middle-class Jewish family, she was an accomplished pianist with a deep love of music, literature, and learning. Pauline believed strongly in education and made sure her children grew up in an intellectually rich environment. It was she who encouraged Albert to learn the violin, an instrument that would remain a lifelong companion. Through her, Albert developed a profound love for classical music, especially the works of Mozart and Bach, which he later described as sources of clarity and inspiration. Albert's younger sister, Maya Einstein, also followed an academic path. Born in 1881, she studied Romance languages and literature and earned a doctorate from the University of Bern. Although she did not pursue a formal academic career, Maya remained intellectually active and deeply connected to Albert's personal and intellectual life. After marrying Swiss philologist Paul Winteler, she lived in Italy and later fled Nazi Germany, eventually joining Albert in Princeton, where she spent her later years.
Together, the Einstein family represented a rare synthesis of technical innovation, cultural depth, and scholarly pursuit. Hermann embodied the spirit of engineering and entrepreneurship, Pauline nurtured artistic and humanistic values, and Maya reflected intellectual discipline in the humanities. This multi-dimensional family environment laid the foundation for Albert Einstein's unique perspective, one that fused scientific rigor with music, philosophy, and a deep concern for humanity. Long before the theories that changed our understanding of the universe, the making of Einstein had already begun. At home.
When he was very young, his parents worried that he had a learning disability because he was very slow to learn to talk. When he was 5 and sick in bed, his father brought him a compass. This sparked his lifelong fascination with electromagnetism. He realized that something deeply hidden had to be behind things. Einstein attended St. Peter's Catholic Elementary School in Munich from the age of 5. When he was 8, he was transferred to the Untold Gymnasium, where he received advanced primary and then secondary school education. Albert briefly remained in Munich to continue his studies, but after several months became disillusioned with the strict rote learning on offer at the gymnasium and convinced both his parents and the school authorities to let him leave to join them in Italy. In 1894, Hermann and Jakob's company tendered for a contract to install electric lighting in Munich, but without success. They lacked the capital that would have been required to update their technology from direct current to the more efficient alternating current alternative. The failure of their bid forced them to sell their Munich factory and search for new opportunities elsewhere. The Einstein family moved to Italy, first to Milan and a few months later to Pavia, where they settled in Palazzo Cornazzani. Einstein, then 15, stayed behind in Munich in order to finish his schooling. His father wanted him to study electrical engineering, but he was a fractious pupil who found the gymnasium's regimen and teaching methods far from congenial. He later wrote that the school's policy of strict rote learning was harmful to creativity. At the end of December 1894, a letter from a doctor persuaded the Luitpold's authorities to release him from its care, and he joined his family in Pavia. While in Italy as a teenager, he wrote an essay entitled On the Investigation of the State of the Ether in a Magnetic Field. Einstein excelled at physics and mathematics from an early age, and soon acquired the mathematical expertise normally only found in a child several years his senior. He began teaching himself algebra, calculus, and Euclidean geometry when he was 12. He made such rapid progress that he discovered an original proof of the Pythagorean theorem before his 13th birthday. A family tutor, Max Talmud, said that only a short time after he had given the 12-year-old Einstein a geometry textbook, the boy had worked through the whole book. He thereupon devoted himself to higher mathematics. Soon the flight of his mathematical genius was so high I could not follow. Einstein recorded that he had mastered integral and differential calculus while still just 14. His love of algebra and geometry was so great that at 12 he was already confident that nature could be understood as a mathematical structure. Although he scored high on the technical exams, Albert was not admitted at this time, in part owing to his youth. The following year, he passed the Swiss Matura, an equivalency exam in the country for those who had not gone through the formal schooling process within Switzerland, but wished to complete the secondary education curriculum there. At 13, when his range of enthusiasms had broadened to include music and philosophy, Talmud introduced Einstein to Kant's critique of pure reason. Kant became his favorite philosopher. According to Talmud, at the time he was still a child, only 13 years old, yet Kant's works, incomprehensible to ordinary mortals, seemed to be clear to him. In 1895, at the age of 16, Einstein sat the entrance examination for the Federal Polytechnic School, later the Eidgenössische Technische Hochschule in Zurich, Switzerland. He failed to reach the required standard in the general part of the test, but performed with distinction in physics and mathematics. On the advice of the Polytechnic's principal, he completed his secondary education at the Argovian Cantonal School, a gymnasium in Aarau, Switzerland, graduating in 1896. While lodging in Aarau with the family of Jost Winteler, he fell in love with Winteler's daughter, Marie. His sister, Maya, later married Winteler's son, Paul.
Earlier that year, he had also renounced his German citizenship to avoid being called up for the required military service expected of all young men in the country. Thus it was that as a stateless individual, he finally entered the Polytechnic School in Zurich in the autumn of 1896, aged 17. There, he would study physics and mathematics, the two subjects which he had demonstrated a prodigious ability in since he was a child.
In January 1896, with his father's approval, Einstein renounced his citizenship of the German Kingdom of Württemberg in order to avoid conscription into military service. The Matura, graduation for the successful completion of higher secondary schooling, awarded to him in September 1896, acknowledged him to have performed well across most of the curriculum, allotting him a top grade of 6 for history, physics, algebra, geometry, and descriptive geometry. At 17, he enrolled in the 4-year mathematics and physics teaching diploma program at the Federal Polytechnic School. He befriended fellow student Marcel Grossmann, who would help him there to get by despite his loose study habits, and later to mathematically underpin his revolutionary insights into physics. Marie Winteler, a year older than him, took up a teaching post in Olsberg, Switzerland. The 5 other Polytechnic School freshmen following the same course as Einstein included just one woman, a 20-year-old Serbian, Mileva Maric. Over the next few years, the pair spent many hours discussing their shared interests and learning about topics in physics that the Polytechnic School's lectures did not cover. In his letters to Maric, Einstein confessed that exploring science with her by his side was much more enjoyable than reading a textbook in solitude. Eventually, the two students became not only friends, but also lovers. Historians of physics are divided on the question of the extent to which Maric contributed to the insights of Einstein's Annus Mirabilis publications. There is at least some evidence that he was influenced by her scientific ideas, but there are scholars who doubt whether her impact on his thought was of any great significance at all. She and Einstein were soon involved in a relationship with each other, and it is now assumed that she contributed to her research, though the exact degree to which she did so is unclear. In any event, her own research was interrupted in the summer of 1901 when she fell pregnant. Maric and Einstein were not yet married by then, and this was a time when having a child out of wedlock was still considered a social scandal. Correspondence between Einstein and Maric, discovered and published in 1987, revealed that in early 1902, while Maric was visiting her parents in Novi Sad, she gave birth to a daughter, Liesl. When Maric returned to Switzerland, it was without the child, whose fate is uncertain. A letter of Einstein's that he wrote in September 1903 suggests that the girl was either given up for adoption or died of scarlet fever in infancy. Einstein and Maric married in January 1903. In May 1904, their son Hans Albert was born in Bern, Switzerland. Their son Eduard was born in Zurich in July 1910. In letters that Einstein wrote to Marie Winteler in the months before Eduard's arrival, he described his love for his wife as misguided and mourned the missed life that he imagined he would have enjoyed if he had married Winteler instead. I think of you in heartfelt love every spare minute, and am so unhappy as only a man can be. Einstein graduated from the Federal Polytechnic School in 1900, duly certified as competent to teach mathematics and physics. His successful acquisition of Swiss citizenship in February 1901 was not followed by the usual sequel of conscription. The Swiss authorities deemed him medically unfit for military service. He found that Swiss schools, too, appeared to have no use for him, failing to offer him a teaching position despite the almost 2 years that he spent applying for one. Eventually, it was with the help of Marcel Grossmann's father that he secured a post in Bern at the Swiss Patent Office as an assistant examiner, level 3. Einstein worked there for the next several years. Beyond serving to support his young family, his work focused on many different devices involving electrical conduction and mechanics, and it has been posited that this impacted on Einstein's own research during his formative years.
The manner in which Einstein burst forth from almost complete obscurity within the developed world's scientific community to become one of Europe's paramount physicists in the mid-1900s is one of the strangest stories in the history of science. Patent applications that landed on Einstein's desk for his evaluation included ideas for a gravel sorter and an electric typewriter. His employers were pleased enough with his work to make his position permanent in 1903, although they did not think that he should be promoted until he had fully mastered machine technology. It is conceivable that his labors at the patent office had a bearing on his development of his special theory of relativity. He arrived at his revolutionary ideas about space, time, and light through thought experiments about the transmission of signals and the synchronization of clocks, matters which also figured in some of the inventions submitted to him for assessment. In 1902, Einstein and some friends whom he had met in Bern formed a group that held regular meetings to discuss science and philosophy. Their choice of the name for their club, the Olympia Academy, was an ironic comment upon its far from Olympian status. Sometimes they were joined by Maritzsch, who limited her participation in their proceedings to careful listening. The thinkers whose works they reflected upon included Henri Poincaré, Ernst Mach, and David Hume, all of whom significantly influenced Einstein's own subsequent ideas and beliefs.
Einstein's first paper, Folgerungen aus den Kapillaritätserscheinungen, conclusions drawn from the phenomena of capillarity, in which he proposed a model of intermolecular attraction that he afterwards disavowed as worthless, was published in the journal Annalen der Physik in 1901. His 24-page doctoral dissertation also addressed a topic in molecular physics. Titled Eine neue Bestimmung der Moleküldimensionen, a new determination of molecular dimensions, and dedicated meinem Freunde Herr Dr. Marcel Grossmann gewidmet, to his friend Marcel Grossmann, it was completed on 30 April 1905 and approved by Professor Alfred Kleiner of the University of Zurich 3 months later. Einstein was formally awarded his Ph.D. on 15 January 1906. 4 other pieces of work that Einstein completed in 1905, his famous papers on the photoelectric effect, Brownian motion, his special theory of relativity, and the equivalence of mass and energy, have led to the year being celebrated as an annus mirabilis for physics, akin to the miracle year of 1666 when Isaac Newton experienced his greatest epiphanies. The publications deeply impressed his contemporaries. The year 1905 would change science forever. In a single year, Einstein published 4 revolutionary papers. 1. Photoelectric effect, proving light behaves as particles. 2. Brownian motion, confirming the existence of atoms. 3. Special relativity, redefining time and space. And 4. E equals mc squared. Energy and mass are interchangeable. This was not incremental progress. This was a scientific earthquake. Time was no longer absolute. Space was no longer fixed. Reality depended on the observer. Consequently, 1905 is usually referred to by biographers of Einstein and historians of Western science as the annus mirabilis, or miracle year of Einstein's career. The first of Einstein's 4 papers of 1905 was entitled On a Heuristic Viewpoint Concerning the Production and Transformation of Light, and was published on the 9th of June. This explained what is known as the photoelectric effect for the first time. The photoelectric effect is where electrons are emitted when electromagnetic radiation, such as light, hits off a material or substance. The electrons which are emitted during such a process are called photoelectrons. Up until 1905, when Einstein described this photoelectric effect, the prevailing view amongst physicists was that light traveled much like a wave in the ocean. But Einstein explained that the photoelectric effect meant that light also traveled in what he termed to be a finite number of energy quanta, which moved without dividing and which could only be absorbed or generated as entities.
This not only explained much that was previously unknown about the nature of light and electrons, but had fundamental implications for understanding how light of a certain frequency could bring sufficient energy into play to liberate an electron. Just 6 weeks after this first paper appeared, Einstein's second paper of 1905, entitled On the Motion of Small Particles Suspended in a Stationary Liquid as Required by the Molecular Kinetic Theory of Heat, was published in Annalen der Physik on the 18th of July. Prior to Einstein's paper, there was no accurate way of measuring the dimensions of molecules, but several scientists in the 19th century, such as John Dalton, had noted that chemical substances tended to combine together or break down in weighted proportions, which suggested that they were all made from an as-yet unidentified physical molecule that was common to all things. These unitary molecules are known as atoms today, after a word which had been coined by ancient Greek philosophers of the 6th century BC, who were themselves seeking to understand the nature of existence, 2.5 millennia before Einstein's time.
In 1907, Einstein proposed a model of matter where each atom in a lattice structure is an independent harmonic oscillator. In the Einstein model, each atom oscillates independently, a series of equally spaced quantized states for each oscillator. Einstein was aware that getting the frequency of the actual oscillations would be difficult, but he nevertheless proposed this theory because it was a particularly clear demonstration that quantum mechanics could solve the specific heat problem in classical mechanics. Peter Debye refined this model. At first glance, the motion seems chaotic. Tiny particles suspended in a liquid jittering endlessly with no clear direction. This phenomenon is known as Brownian motion, the random movement of microscopic particles drifting through a fluid or gas. Rather than moving smoothly, each particle follows an unpredictable path. It vibrates within a small region, pauses, then suddenly shifts into another microscopic space, only to repeat the same restless dance again. This motion does not favor any direction. The fluid itself remains in thermal equilibrium, meaning its overall momentum stays balanced, even though its smallest components are in constant motion. At the molecular level, this restless activity is a consequence of heat. Countless invisible molecules collide with the suspended particle from all sides. Each impact is tiny, but together they produce a motion that never truly stops. The energy driving this process is part of the fluid's internal energy, shared equally among molecular motion, rotation, and vibration, as described by the equipartition theorem. The story of Brownian motion begins in 1827, when Scottish botanist Robert Brown peered through a microscope at pollen grains floating in water. To his surprise, the particles appeared alive, darting and trembling without explanation. Brown carefully documented the motion, though its cause remained a mystery for decades. In 1900, French mathematician Louis Bachelier took an abstract leap forward. In his doctoral thesis, The Theory of Speculation, supervised by Henri Poincaré, he introduced a mathematical framework for random motion, what would later become known as the Wiener process, the foundation of modern Brownian motion theory.
Then came a decisive breakthrough. In 1905, a young theoretical physicist named Albert Einstein published a paper that transformed the phenomenon from curiosity into proof. Einstein proposed that the particles were being bombarded by individual water molecules, entities too small to be seen but powerful enough in numbers to drive the motion. The constant imbalance of these molecular collisions explained why the particle's direction changed endlessly, creating the illusion of randomness. Einstein's explanation did more than describe motion. It provided compelling evidence that atoms and molecules truly exist. That proof was confirmed experimentally in 1908 by French physicist Jean Perrin, whose meticulous measurements matched Einstein's predictions. Perrin's work settled a long-standing debate about the atomic nature of matter and earned him the 1926 Nobel Prize in Physics for revealing the discontinuous structure of matter. Yet, despite its simple appearance, Brownian motion hides immense complexity. The interactions of countless molecules cannot be solved by tracking each one individually. Instead, scientists rely on probabilistic and statistical models, treating molecular behavior as populations rather than individuals. Einstein and Marian Smoluchowski developed foundational models in statistical mechanics, while later mathematicians refined purely probabilistic approaches known as stochastic processes. From simple random walks to advanced limit theorems like Donskoy's theorem, these models converge toward the same remarkable conclusion. Order can emerge from randomness, and randomness itself can be described by precise mathematical laws. Brownian motion, once observed as a trembling pollen grain, became one of the strongest bridges between mathematics, physics, and the unseen atomic world. Einstein's third paper was published just over 2 months later, on the 26th of September 1905. This was entitled On the Electrodynamics of Moving Bodies and focused on the issue of special relativity. This sought to reconcile an equation which the Scottish mathematician and scientist James Clerk Maxwell had devised in the early 1860s regarding electricity and magnetism. Maxwell's equations led to difficulties in how physicists should understand mechanics which occurred close to the speed of light. In response to this problem, Einstein outlined his special theory of relativity, or special relativity, in his 1905 paper. This stated that the speed of light is the same for all observers, regardless of the motion of the light source or the observer of the light source. This opposed the idea postulated over 2 centuries earlier by Isaac Newton, which held that the speed of light is not fixed. Moreover, Einstein's special theory of relativity correctly assumed that when 2 objects are involved concerning light, there is no true way of knowing which is in motion and which is not. Relativity is the theory that governs a universe far beyond everyday experience. A universe where objects move at extraordinary speeds, and reality itself begins to behave differently. At its heart, relativity overturns one of humanity's oldest assumptions, that time flows the same everywhere. Instead, Einstein revealed a startling truth. Time flows differently for every moving object. Time is measured by clocks, and in relativity, clocks do not agree. A clock in motion ticks more slowly than one at rest. At ordinary speeds, this effect is far too small to notice, but as motion approaches the speed of light, the difference becomes profound. Events that appear simultaneous to one observer no longer occur at the same moment for another who is moving. Near light speed, many physical phenomena simply cannot be understood without the rules of special relativity. What makes this theory remarkable is not its complexity, but its elegance. Unlike many modern theories in physics, special relativity requires only high school-level mathematics, yet it completely reshapes our understanding of space, time, and motion. From just 2 simple postulates, a cascade of extraordinary consequences emerges. The first is the principle of relativity. It states that the laws of physics are the same for all observers moving at constant speeds relative to one another. There is no absolute state of rest. An observer on a smoothly moving train experiences the same physical laws as someone standing still. Inside the train, nature behaves exactly as it would if the train were not moving at all. The second postulate is even more radical. The speed of light is constant. No matter how fast an observer is moving, light always travels at the same speed.
A person standing on a platform and a passenger aboard a speeding train will both measure light traveling at exactly the same velocity, even if the light comes from the moving train itself. Together, these two ideas force a redefinition of what we mean by speed. In everyday life, speed is simple, distance divided by time. But in special relativity, this formula is no longer enough. The speed of light becomes the ultimate limit, the maximum speed allowed by nature. Even if a moving clock measures 10 times more distance in the same amount of time, the speed observed from the ground does not increase by a factor of 10. Space and time themselves adjust to preserve the cosmic speed limit. In Einstein's universe, motion reshapes time, simultaneity dissolves, and the familiar rules of intuition give way to deeper laws. Special relativity shows us that reality is not fixed, but depends on how fast you move through it. Einstein's fourth and final paper of his Annus Mirabilis was published on the 21st of November and was entitled, "Does the Inertia of a Body Depend Upon Its Energy Context?" Few have heard of that title today, but a great many are familiar with the equation which Einstein pioneered in the paper, E equals mc squared. In brief, what this means is that the energy of a body at rest, defined as E, is equal to its mass, or m, multiplied by the speed of light, the c of the equation, squared. This equivalency equation showed that a massive particle possesses an energy, or rest energy, which is distinct from the kinetic energy of a particle. This would come to be known as the mass-energy equivalence, and highlights how the rest energy of a particle, such as the nucleus of an atom, could be so massive as to result in an enormous amount of light and thermal energy being released if the particle was disturbed sufficiently. Mass-energy equivalence reveals one of the most profound truths in modern physics. Mass itself is a form of energy. Even when an object is perfectly still, it carries an enormous amount of intrinsic energy simply by existing. In the object's rest frame, where it has no motion and no momentum, mass and energy are directly related. They differ only by a constant factor, the speed of light squared. This relationship is captured in one of the most famous equations in science, E equals mc squared. In classical Newtonian mechanics, a stationary object has no kinetic energy. Any energy it possesses must come from other sources, chemical bonds, heat, or its position within a force field. Compared to mass energy, these forms are tiny. For just 1 kilogram of matter, the energy equivalent of its mass is on the order of 10 to the 17th joules, an amount far beyond anything encountered in everyday life. This principle becomes unmistakably real in nuclear reactions. When atoms undergo nuclear fission or fusion, the total mass of the resulting atoms is slightly less than the mass of the original ones. The missing mass does not vanish, it is transformed into energy, released as intense heat, radiation, and light. In these extreme events, Einstein's equation allows physicists to calculate the energy released by measuring the tiny change in mass. Relativity goes even further. In Einstein's framework, all energy that moves with an object contributes to its mass, not just the matter itself. Mass becomes a measure of how strongly an object resists acceleration, and energy adds to that resistance. Imagine a perfectly sealed box lined with ideal mirrors, trapping light inside. Photons have no rest mass, yet the box would weigh more with the light inside than without it. The energy of the trapped light contributes to the total mass of the system by an amount equal to its energy divided by c squared. From the perspective of an observer at rest, removing energy from a system is equivalent to removing mass. The equation m equals E divided by c squared tells us exactly how much mass disappears when energy escapes. Likewise, adding energy to an isolated system increases its mass by the same proportion. Mass and energy are not separate entities. They are two expressions of the same physical reality.
Through this insight, Einstein revealed that matter is not solid and immutable, but condensed energy, bound together by the deepest laws of the universe.
His research shaped the application of science to the modern world in the decades that followed. For instance, when you walk up to an automatic door today and it opens in front of you, this is because the sensors used in the doorway react when the photons in the light beams they emit are obstructed, in this case by a moving person. The sensor then tells the door to open. Einstein first explained how photons work. Solar-powered calculators and streetlights that automatically turn on when it gets dark, amongst other innovations, also emerged from his work on light. The special theory of relativity helped lead to the development of global positioning systems, or GPS, over time. Thus, when you switch on Google Maps, it is effectively functioning based partly on research which Einstein published in his Annus Mirabilis papers. And when a nuclear power plant creates massive amounts of energy by harnessing the energy in the nucleus of an atom, they are doing so based on Einstein's discoveries concerning energy and mass equivalence as contained in the equation E equals mc squared. Einstein's groundbreaking research findings, published in 1905, soon came to the attention of the European scientific community, though at a time when people were still reliant on the circulation of hard copies of academic journals and word of mouth for research to be disseminated, it took a few years for the import of his findings to become clear across Europe. In 1907, Albert Einstein reached a turning point in his quest to extend special relativity into a new theory of gravitation. That year, he formulated what he later called the happiest thought of my life, the equivalence principle. It proposed a radical idea. An observer, sealed inside a box, falling freely under gravity, would feel weightless and be unable to detect the gravitational field at all. In free fall, gravity seemed to disappear. This insight suggested something extraordinary, that gravity was not a conventional force, but a deeper feature of nature itself. Einstein's sabbatical as a civil servant approached its end in 1908, when he secured a junior teaching position at the University of Bern. In 1911, a lecture on relativistic electrodynamics that he gave at the University of Zurich, much admired by Alfred Kleiter, led to Zurich's luring him away from Bern with a newly created associate professorship. Promotion to a full professorship followed in April 1911, when he took up a chair at the German Charles Ferdinand University in Prague, a move which required him to become an Austrian citizen of the Austro-Hungarian Empire, which was not completed. His time in Prague saw him producing 11 research papers. From 30 October to 3 November 1911, Einstein attended the first Solvay Conference on Physics. In 1911, Einstein used the equivalence principle to make a bold prediction. He calculated that light from a distant star should bend as it passed close to the sun, deflected by the sun's gravitational pull near its visible surface, the photosphere. Light, he argued, did not simply travel in straight lines, it followed paths shaped by gravity. In July 1912, he returned to his alma mater, the ETH Zurich, to take up a chair in theoretical physics. His teaching activities there centered on thermodynamics and analytical mechanics, and his research interests included the molecular theory of heat, continuum mechanics, and the development of a relativistic theory of gravitation. In his work on the latter topic, he was assisted by his friend Marcel Grossmann, whose knowledge of the kind of mathematics required was greater than his own. In the spring of 1913, two German visitors, Max Planck and Walter Nernst, called upon Einstein in Zurich in the hope of persuading him to relocate to Berlin. They offered him membership of the Prussian Academy of Sciences, the directorship of the planned Kaiser Wilhelm Institute for Physics, and a chair at the Humboldt University of Berlin that would allow him to pursue his research supported by a professorial salary but with no teaching duties to burden him.
He duly joined the Academy on 24 July 1913 and moved into an apartment in the Berlin district of Dahlem on April 1, 1914. He was installed in his Humboldt University position shortly thereafter. In 1913, Einstein refined his approach. He had found the mathematical language capable of expressing his vision, Riemann geometry, describing a curved, non-Euclidean four-dimensional spacetime. Using the Riemann curvature tensor, he could now model gravitation not as a force, but as the curvature of spacetime itself. By the autumn of 1915, Einstein's long struggle reached its climax. The mathematical framework of general relativity was complete. With it, he revisited the bending of light by the sun, now with greater precision, and turned to a long-standing astronomical mystery, the precession of Mercury's perihelion, the slow drift of the point where Mercury comes closest to the sun. Newton's laws could not fully explain it. Einstein's equations could, and they matched observation exactly. But theory alone was not enough. Proof would have to come from the sky. On 29 May 1919, a total solar eclipse offered a rare opportunity. During the brief darkness, stars near the sun became visible, allowing astronomers to test whether their light was bent by the sun's gravity. The task fell to British astronomer Sir Arthur Eddington, who led expeditions to observe the eclipse from remote locations. The results were astonishing. The measured deflection of starlight closely matched Einstein's predictions. When Einstein's findings were announced, they made headlines around the world. On 7 November 1919, the Times of London declared in bold letters, "Revolution in science, new theory of the universe, Newtonian ideas overthrown." In a single moment, Einstein was transformed from a respected physicist into a global icon, and humanity's understanding of gravity, space, and time was forever changed. For years, tensions had been building between the major European powers over issues as disparate as colonial rivalry in Africa, the vacuum left by the collapse of Ottoman power in the Balkans, and the naval race between Britain and Germany. These all coalesced in the summer of 1914 into the outbreak of a pan-European war, which soon became a worldwide conflict. The outbreak of the First World War in July 1914 marked the beginning of Einstein's gradual estrangement from the nation of his birth. When the Manifesto of the 93 was published in October 1914, a document signed by a host of prominent German thinkers that justified Germany's belligerence, Einstein was one of the few German intellectuals to distance himself from it and sign the alternative, Irenic Manifesto to the Europeans instead. However, this expression of his doubts about German policy did not prevent him from being elected to a 2-year term as president of the German Physical Society in 1916. When the Kaiser Wilhelm Institute for Physics opened its doors the following year, its foundation delayed because of the war, Einstein was appointed its first director, just as Planck and Nernst had promised. Einstein was elected a foreign member of the Royal Netherlands Academy of Arts and Sciences in 1920 and a foreign member of the Royal Society in 1921. In 1922, he was awarded the 1921 Nobel Prize in Physics for his services to theoretical physics and especially for his discovery of the law of the photoelectric effect. At this point, some physicists still regarded the general theory of relativity skeptically, and the Nobel citation displayed a degree of doubt even about the work on photoelectricity that it acknowledged. It did not assent to Einstein's notion of the particulate nature of light, which only won over the entire scientific community when S. N. Bose derived the Planck spectrum in 1924. That same year, Einstein was elected an international honorary member of the American Academy of Arts and Sciences.
Britain's closest equivalent of the Nobel Award, the Royal Society's Copley Medal, was not hung around Einstein's neck until 1925. He was elected an international member of the American Philosophical Society in 1930.
Given all of this, it is perhaps unsurprising that in 1921, the Nobel Foundation in Stockholm decided to award Einstein the Nobel Prize for Physics. They specifically cited his work in discovering the photoelectric effect in his paper from 1905 in the award designation, but it could just as easily have been awarded for a wide range of research findings over the previous 15 or so years. Receipt of the Nobel Prize in 1921 and the opening up of the world during the Bundesheim years of the 1920s after years of war and social discord saw Einstein and Elsa, whom he had just recently married, decide to travel internationally. In early April 1921, they sailed into New York City, where the couple were greeted by the mayor, John Francis Hylan, and a delegation of some of the most senior members of the city's Jewish community. Weeks of lectures and receptions followed, notably at Columbia University in New York and Princeton University in New Jersey. Later that month, Einstein met President Warren Harding in the White House. Afterwards, they left for a Pacific voyage to the Empire of Japan and then onwards to Singapore and India before reaching the Middle East. There, Einstein visited Palestine, which had become subject to a British mandate following the end of the First World War, and where the Jewish Zionist movement was attempting to establish a new state for the world's Jews after centuries of being scattered around the globe. Afterwards, he returned to Germany, but the 1921 to 1922 trip was the beginning of a pattern of significant trips to different parts of the world. For instance, in 1925, he visited South America, spending weeks in Argentina, Uruguay, and Brazil, countries which were booming economically and socially in the early 20th century and where Einstein was revered within the academic community. In the mid-1920s, Einstein became involved in a scientific debate which was widely reported on at the time.
This was between himself and Niels Bohr, a Danish physicist who had won the Nobel Prize in Physics in 1922, 12 months after Einstein had been awarded the same honor. A dispute had been building between Einstein and Bohr throughout the mid-1920s over their differing interpretations of quantum theory. Much of this centered on Bohr's refusal to believe that photons, which Einstein had first theorized the existence of in 1905, were real. He did not accept that they did exist until 1925, and even then their debates raged on over other elements of their respective views on quantum mechanics. Debates were held in London and elsewhere between 1922 and 1925, but culminated in a famous academic disputation in 1927 at the Fifth Solvay Conference at the International Solvay Institutes of Physics and Chemistry in Brussels. Here, Bohr and Einstein continued their debate, with both figures arguing points which eventually proved to be accurate. However, beyond the theoretical arguments, the conference is noteworthy for the number of the world's most accomplished physicists it drew together. 17 of the 29 attendees had already or later received Nobel Prize awards, while Einstein and Bohr were joined by figures including Marie Curie, Werner Heisenberg, and Erwin Schrödinger. It points to the sheer level of brilliance of the European scientific community in the interwar period. The late 1920s also saw Einstein reconceptualizing his own theories of the universe. This was in response to the discovery by the American astronomer Edwin Hubble of the recession of the nebulae, or what is now termed Hubble's law. This states that galaxies are moving away from Earth at speeds which are proportionate to the distance they are from the Milky Way. These speeds are always faster, meaning that the further a cosmic body is from the Earth, the faster it will move away from the Earth. These findings, which were made public in 1929, required Einstein to abandon his current theory of the universe at that time, which was known as the cosmological constant, which supposed that the universe was largely static in the way that it expanded, i.e., that the cosmos had been expanding since the Big Bang at a relatively constant speed. Hubble's discoveries forced Einstein to re-evaluate his hypothesis, as it was now clear that the universe was expanding at an ever greater speed.
Hubble's discovery was also partly responsible for Einstein's decision to embark on a new journey to the United States in December 1930.
In December 1930, Einstein began another significant sojourn in the United States, drawn back to the U.S. by the offer of a 2-month research fellowship at the California Institute of Technology. Caltech supported him in his wish that he should not be exposed to quite as much attention from the media as he had experienced when visiting the U.S. in 1921, and he therefore declined all the invitations to receive prizes or make speeches that his admirers poured down upon him. But he remained willing to allow his fans at least some of the time with him that they requested. After arriving in New York City, Einstein was taken to various places and events, including Chinatown, a lunch with the editors of the New York Times, and a performance of Carmen at the Metropolitan Opera, where he was cheered by the audience on his arrival. During the days following, he was given the keys to the city by Mayor Jimmy Walker and met Nicholas Murray Butler, the president of Columbia University, who described Einstein as the ruling monarch of the mind. Harry Emerson Fosdick, pastor at New York's Riverside Church, gave Einstein a tour of the church and showed him a full-size statue that the church made of Einstein standing at the entrance. Also during his stay in New York, he joined a crowd of 15,000 people at Madison Square Garden during a Hanukkah celebration. Einstein next traveled to California, where he met Caltech president and Nobel laureate Robert A. Millikan. His friendship with Millikan was awkward, as Millikan had a penchant for patriotic militarism, where Einstein was a pronounced pacifist. During an address to Caltech students, Einstein noted that science was often inclined to do more harm than good. This aversion to war also led Einstein to befriend author Upton Sinclair and film star Charlie Chaplin, both noted for their pacifism. Carl Laemmle, head of Universal Studios, gave Einstein a tour of his studio and introduced him to Chaplin. They had an instant rapport, with Chaplin inviting Einstein and his wife, Elsa, to his home for dinner. Chaplin said Einstein's outward persona, calm and gentle, seemed to conceal a highly emotional temperament, from which came his extraordinary intellectual energy. Chaplin's film, City Lights, was to premiere a few days later in Hollywood, and Chaplin invited Einstein and Elsa to join him as his special guests. Walter Isaacson, Einstein's biographer, described this as one of the most memorable scenes in the new era of celebrity. Chaplin visited Einstein at his home on a later trip to Berlin and recalled his modest little flat and the piano at which he had begun writing his theory. Chaplin speculated that it was possibly used as kindling wood by the Nazis. Einstein and Chaplin were cheered at the premiere of the film. Chaplin said to Einstein, "They cheer me because they understand me, and they cheer you because no one understands you." In February 1933, while on a visit to the United States, Einstein knew he could not return to Germany with the rise to power of the Nazis under Germany's new chancellor, Adolf Hitler. While at American universities in early 1933, he undertook his third 2-month visiting professorship at the California Institute of Technology in Pasadena. In February and March 1933, the Gestapo repeatedly raided his family's apartment in Berlin. He and his wife Elsa returned to Europe in March, and during the trip they learned that the German Reichstag had passed the Enabling Act on 23 March, transforming Hitler's government into a de facto legal dictatorship, and that they would not be able to proceed to Berlin. Later on, they heard that their cottage had been raided by the Nazis and Einstein's personal sailboat confiscated. Upon landing in Antwerp, Belgium on 28 March, Einstein immediately went to the German consulate and surrendered his passport, formally renouncing his German citizenship. The Nazis later sold his boat and converted his cottage into a Hitler youth camp. In 1939, a group of Hungarian scientists that included émigré physicist Leo Szilard attempted to alert Washington, D.C. to ongoing Nazi atomic bomb research. The group's warnings were discounted. Einstein and Szilard, along with other refugees such as Edward Teller and Eugene Wigner,
regarded it as their responsibility to alert Americans to the possibility that German scientists might win the race to build an atomic bomb, and to warn that Hitler would be more than willing to resort to such a weapon. To make certain the U.S. was aware of the danger, in July 1939, a few months before the beginning of World War II in Europe, Szilard and Wigner visited Einstein to explain the possibility of atomic bombs, which Einstein, a pacifist, said he had never considered. He was asked to lend his support by writing a letter with Szilard to President Franklin D. Roosevelt, recommending the U.S. pay attention and engage in its own nuclear weapons research. The letter is believed to be arguably the key stimulus for the U.S. adoption of serious investigations into nuclear weapons on the eve of the U.S. entry into World War II. In addition to the letter, Einstein used his connections with the Belgian royal family and the Belgian Queen Mother to get access with a personal envoy to the White House's Oval Office. Some say that as a result of Einstein's letter and his meetings with Roosevelt, the U.S. entered the race to develop the bomb, drawing on its immense material, financial, and scientific resources to initiate the Manhattan Project.
Eventually, in mid-July 1945, the world's first nuclear device was detonated in the desert of New Mexico. By the time the first nuclear weapon was detonated, the Second World War had already been over in Europe for several weeks. However, because of the agreed Allied policy of leaving the conclusion of the war in the Pacific against the Empire of Japan until after Nazi Germany had been defeated, the conflict was still raging there by the summer of 1945. Accordingly, the administration of President Harry Truman quickly decided to use the new weapon against Japan in the belief that doing so would ultimately save over 1 million lives if it forced Japan to surrender quickly. Thus, on the 6th of August, 1945, the first nuclear weapon used in warfare was dropped on the city of Hiroshima, killing upwards of 75,000 people on the first day and a further 60,000 or so in the months that followed from radiation sickness. 3 days later, a second nuclear device of a slightly different kind was dropped on the city of Nagasaki, killing upwards of 80,000 people across the initial destruction zone and as a result of the after effects. Japan did quickly surrender, but Einstein was appalled by the ferocity of the attacks and the fallout from them. Shortly after the bombings, he declared that the time has come now when man must give up war. It is no longer rational to solve international problems by resorting to war. He subsequently expressed his regret that his research on the molecular structure of the world and the concept of mass, energy, and equivalence, which he had first published in 1905, had contributed towards the development of the nuclear weapons. For Einstein, war was a disease. He called for resistance to war. By signing the letter to Roosevelt, some argue he went against his pacifist principles. In 1954, a year before his death, Einstein said to his old friend Linus Pauling, "I made one great mistake in my life when I signed the letter to President Roosevelt recommending that atom bombs be made. But there was some justification, the danger that the Germans would make them." Einstein became an American citizen in 1940. Not long after settling into his career at the Institute for Advanced Study in Princeton, New Jersey, he expressed his appreciation of the meritocracy in American culture compared to Europe. He recognized the right of individuals to say and think what they pleased without social barriers. As a result, individuals were encouraged, he said, to be more creative, a trait he valued from his early education. Einstein joined the National Association for the Advancement of Colored People in Princeton, where he campaigned for the civil rights of African Americans. He considered racism America's worst disease, seeing it as handed down from one generation to the next. As part of his involvement, he corresponded with civil rights activist W.E.B. Du Bois and was prepared to testify on his behalf during his trial as an alleged foreign agent in 1951. When Einstein offered to be a character witness for Du Bois, the judge decided to drop the case. In 1946, Einstein visited Lincoln University in Pennsylvania, a historically black college, where he was awarded an honorary degree. Lincoln was the first university in the United States to grant college degrees to African Americans. Alumni include Langston Hughes and Thurgood Marshall. Einstein gave a speech about racism in America, adding, "I do not intend to be quiet about it." A resident of Princeton recalls that Einstein had once paid the college tuition for a black student. Einstein has said, "Being a Jew myself, perhaps I can understand and empathize with how black people feel as victims of discrimination." Isaacson writes that when Marian Anderson, the black contralto, came to Princeton for a concert in 1937, the Nassau Inn refused her a room. So Einstein invited her to stay at his house on Main Street in what was a deeply personal as well as symbolic gesture. Whenever she returned to Princeton, she stayed with Einstein, her last visit coming just 2 months before he died. Shortly after the end of the Second World War, he had begun to suffer from an abdominal aortic aneurysm, an enlargement of the abdominal aorta, the largest artery in the abdomen. It can become blocked, much like any other part of the circulatory system, owing to high blood pressure, high cholesterol, and smoking. Einstein had the issue operated on successfully in 1948 by reinforcing the aorta wall, but despite improving his lifestyle, including adopting a vegetarian diet. On 17 April 1955, Einstein experienced internal bleeding caused by the rupture of an abdominal aortic aneurysm, which had previously been reinforced surgically by Rudolf Nissen in 1948. He took the draft of a speech he was preparing for a television appearance commemorating the State of Israel's 7th anniversary with him to the hospital, but he did not live to complete it. Einstein refused surgery, saying, "I want to go when I want. It is tasteless to prolong life artificially. I have done my share. It is time to go. I will do it elegantly." He died in the Princeton Hospital early the next morning at the age of 76, having continued to work until near the end. During the autopsy, the pathologist Thomas Stoltz Harvey removed Einstein's brain for preservation without the permission of his family, in the hope that the neuroscience of the future would be able to discover what made Einstein so intelligent. Einstein's remains were cremated in Trenton, New Jersey, and his ashes were scattered at an undisclosed location. In a memorial lecture delivered on 13 December 1965 at UNESCO's headquarters, nuclear physicist J. Robert Oppenheimer summarized his impression of Einstein as a person. He was almost wholly without sophistication and wholly without worldliness. There was always with him a wonderful purity at once childlike and profoundly stubborn. Einstein bequeathed his personal archives, library, and intellectual assets to the Hebrew University of Jerusalem in Israel. Albert Einstein stands as one of the most influential thinkers in the history of science. Over the course of half a century, his discoveries reshaped humanity's understanding of reality so profoundly that his name itself became synonymous with genius. What makes this legacy all the more remarkable is how humbly it began. In the 1890s, Einstein's life was anything but stable. As a teenager and young man, he became something of an intellectual nomad, moving between Germany, Italy, and Switzerland as his parents struggled to balance financial uncertainty with their growing recognition of their son's extraordinary abilities in mathematics and physics. These years of displacement would quietly shape his independent spirit and resistance to authority. A sense of stability finally arrived at the Polytechnic School in Zurich, but it did not bring immediate success. When Einstein completed his studies, the great universities of Central Europe saw no reason to hire him. Instead, he found himself working as a technical examiner at the Swiss Patent Office in Bern, a modest position far removed from academic prestige. Yet it was there, reviewing patent applications by day and raising a young family by night, that Einstein began quietly rewriting the foundations of physics.
In 1905, his Annus Mirabilis, the Miracle Year, Einstein published 4 revolutionary papers. Together, they transformed humanity's understanding of light, matter, energy, space, and time. They revealed the existence of photons, explained the atomic nature of matter, and introduced ideas that would ultimately unlock nuclear energy. Physics would never be the same again.
From that moment on, Einstein's ascent was swift. Year after year, he rose through the academic ranks until he reached the pinnacle of European science in Berlin, just as the world was sliding into the catastrophe of World War I. Amid the chaos of that conflict, Einstein completed his greatest intellectual achievement, the general theory of relativity, a radical new description of gravity as the curvature of spacetime itself. In 1921, he was awarded the Nobel Prize in Physics, and international acclaim followed. But from the 1920s onward, Einstein became more than a scientist. He became a global public figure. He traveled widely from the United States to South America, across Europe and the Middle East, using his fame to speak out on issues far beyond physics. Most urgently, he warned of the growing threat posed by Nazi Germany. When Adolf Hitler seized power in 1933, Einstein immediately renounced his German citizenship and fled to the United States. There, he continued to raise alarms about the possibility of the Nazis developing nuclear weapons. Yet for Einstein, the committed pacifist, history delivered a cruel paradox. The race to defeat Nazi Germany in nuclear physics culminated not in peace, but in the atomic bombings of Hiroshima and Nagasaki in 1945. In the war's aftermath, Einstein used his influence to advocate for a Jewish homeland in the Middle East, shaped by the moral catastrophe of the Holocaust. When he died in 1955, he was widely regarded as the most celebrated scientist in the world, a thinker whose ideas had permanently transformed physics, mathematics, and cosmology, and whose moral voice resonated far beyond the laboratory. The history of the 20th century might have unfolded very differently without Albert Einstein. So what do you think? Was Einstein the most revolutionary intellectual of the modern era? And what might explain the extraordinary depth of his intellect? Let us know your thoughts in the comments below, and thank you very much for watching.